Good morning and welcome to this next lecture on sound and structural vibration. We have been looking at a coupled structural acoustic waveguide behavior, and we started deriving the equations for the acoustic fluid, for the bottom boundary plate and the connecting continuity boundary condition. So we stopped over here. I continue with this derivation. We stopped over here. I'll continue with this derivation. Okay. So now so this is the condition at the bottom part. Okay, this is the boundary condition at the bottom edge, bottom surface of a lower boundary. Let me call it lower boundary. Okay. What about at the top boundary? At the top boundary, the wall is rigid. The wall is rigid. Okay. So what we will have is del P by del Y at Y equal to A will be 0. Okay. This from acoustics. So what does that give me? Minus I K Y A. So I am doing del P del Y at Y equal to A. Okay, I am not writing the P equation again, I am just writing the derivative. Minus I K Y A e to the power minus I K Y small a plus I K Y B e to the power of I K Y A e to the power of minus I K X X is equal to 0. So this is the boundary condition at the top boundary. This is the boundary condition at the lower boundary. This is the boundary condition at the top boundary. So this is equation equated to 0. So this can be removed, and therefore we get a relationship between A and B. Okay. So the I can go. So the I can go, KY can go. Okay. So what we now get is the A is related to B as e to the power of I twice KY A. Okay. So if we replace the A here using this condition over here, what do we get? We get W of X is equal to B I K Y e to the power of minus I K X X into 1 minus e to the power of I twice K Y A divided by omega square rho okay. Now this is W of X. Okay. Now what did we have? So what is remaining now? What is remaining now? We have to bring this Wx into the plate. We have to utilize the plate equation. Okay. So plate equation, let me just remind you that The pressure is P x comma y. If I don't write the time term, is A e to the power minus I k x x minus I k y y plus B e to the power of minus I k x x e to the power plus I k y y. Okay, and there is the panel equation, which is E h cube by 12 into 1 minus nu square, okay, minus m omega square w of x is equal to minus p at x comma 0. Okay, so this is equal to, if I write pressure, this is equal to A e to the power of, or let me say here, A plus B e to the power of minus I k x x. d4 w of x dx4 minus m omega square w of x. Okay, this is what it is. Okay, and then w of x is what? W of x is some, let's say, capital W, okay, e to the power of I omega t minus ki kp of x. Okay, so the displacement W is some W amplitude e to the power I omega t minus I kp x. Now from the first problem, classical problem, we know that this kpx must be equal to kxx. Okay, this kp must be equal to kx. Okay, so this is equal to some W e to the power of let's keep the time here, e to the power I omega t minus I kp x. Okay, I'm sorry, let's kxx. Okay, so now if I decide to drop the time term, okay, decide to drop the time term, my w of x is equal to this w e to the power of minus I k x x, and d4w dx4 is equal to kx to the power 4th w e to the power of minus I kx x, okay, which is equal to kx to the power 4th w of x. So this term here, okay, is this term here, and I'm going to replace it with this. So it's also going to have w of x, and there is a w of x in the time derivative term, so we'll keep it out. Okay. So what do we have? We have E h cube by 12 into 1 minus nu square, okay, k x to the power 4th minus m omega square into w of x is equal to, now the pressure at x equal to 0, I mean pressure at y equal to 0 applied to the plate, and we also had a relation between B and A. So we get, if we write this pressure only in terms of B, I get minus B e to the power of minus I k x x into 1 plus e to the power of I twice k y a. Okay. So now Wx was also known, right? Wx was also known. So what was Wx? Let me remind you. Wx we found out was B I k y e to the power of minus I k x x into 1 minus e to the power of I twice k y a. Okay. So this will be substituted here, this will be substituted here, and you have B on the left, you have B on the right, so B disappears. Okay, so what happens now? So this portion I will club it as I and not keep repeating it. So I write EI kx fourth minus m omega square, okay, I k y into 1 minus e to the power of I twice k y a by omega square rho is equal to minus 1 plus e to the power of I twice k y a. Okay, so you can see that B got cancelled. You can see that B got cancelled. You can see e to the power of minus I k x also got cancelled. So just this I k y survives and these terms, exponent terms, survive. Okay, so if we try to make it even brief or smaller, EI kx fourth minus m omega square is equal to minus omega square rho by ky cot. So this happens to be a cot of kya. Okay. So if I have shortened some steps, if I bring this to the denominator of this and simplify, it is cot kya. Okay. So I can rearrange this in a few ways for my advantage. Okay. So one is this. Now from the classical problem I will just use it, KB, which is the free wave number in the panel, in the plate is given by KB is equal to m omega square by EI to the power 1/4. This is the free in vacuo flexural wave number in the plate. Okay. So here I have m omega square, here I have EI. So if I divide by EI, what do I get? Let us see. So I get EI, I take outside. So EI kx fourth minus m omega square by EI. Okay, so this will become KB fourth, right? We'll write this again. Okay, so that is equal to my minus omega square rho by ky cot of kya. This is the acoustic density, acoustic fluid density. Okay. Now if I take EI to the other side, I get kx fourth minus kb to the power fourth, okay, is equal to minus omega square rho by EI ky cot of kya. Okay, so if I multiply by m and divide by m, so if I multiply by m, let's say multiply by m and divide by m, then this term here is kb fourth. Okay, so what do I get? I get minus kb fourth, okay, then rho, I multiply by one extra a, okay, and therefore I divide by one extra a, and I have this ky here and this m here, and the cot kya. So how does it look? It looks like this: kx fourth minus kb fourth is equal to minus kb fourth rho into a divided by m into cot of kya by ky. Now we can divide by kb fourth. Okay, so then what do we have? I can write this equation as kx fourth by k b fourth is equal to 1 minus rho a by m cot of kya by kya. Okay, so this is one level. Now we'll do a non-dimensionalization. Okay, we'll do a non-dimensionalization. We'll non-dimensionalize this. So how do we do that? We will bring in a non-dimensional omega, which is omega divided by omega coincidence, okay, which is wave number acoustic by acoustic, the coincidence wave number. Okay, so this will be the non-dimensional frequency. Okay, then we'll bring in a lambda. Okay, we will call it wave number at coincidence times a. So this is a non-dimensional fluid height. Non-dimensional fluid height. We'll bring in an epsilon, which is fluid density height by the mass per unit area of the panel, which is the fluid loading parameter. It's very important parameter. Okay, it's a very important parameter. Okay, then this xi, I think, is the coupled wave number divided by the wave number at coincidence. Then we have chi, which is the coupled wave number to the acoustic wave number, which is also xi over omega. Okay, so these are the non-dimensional parameters. If we use this non-dimensional parameters, okay, and we non-dimensionalize this equation over here, we non-dimensionalize this equation over here, okay, we'll get this equation xi fourth by omega square minus 1 into lambda square root of omega square minus xi square tan lambda square root of omega square minus xi square plus epsilon equal to 0. Okay, I'll show you how this happens. It's very simple, there's nothing to it, and in a way, if you have had acoustics, you should be able to do this. But I'll substitute these non-dimensional parameters in this equation and get you to see that this happens over here. Okay, I'll just say a few words and stop because time is running out. So epsilon is the fluid loading parameter. That means the parameter that says that the structure is in contact with the fluid, influenced by the fluid, or fluid is in contact with the structure, influenced by the structure. So if epsilon is set to 0, if epsilon is set to 0, that means there is no coupling. Okay, so this is an equation which is an uncoupled dispersion equation. Uncoupled dispersion equation. Okay. So when you set this to 0 as it is happening here, what do you expect? You expect to see uncoupled waves. Uncoupled waves. Okay. So you can see that over here. Either this term has to be 0, or this term has to be 0, or this tan term has to be 0. Only then the right is 0. If you set this, let us call it 1, 2 and 3. Okay. If you set 1 to 0, you will see the flexural wave, uncoupled flexural wave in the plate. Okay. You can already see the square on the omega and 4th power on the wave number. Okay, that's flexural wave. If you set 2 to 0, you will get the plane wave. You will get the plane wave in the sound field. And if you set 3 to 0, you will get the acoustic cut-ons. You will get the acoustic cut-ons. So by setting epsilon to 0, you see the uncoupled waves, and therefore when you have an epsilon, what would be the coupled waves? So this equation tells you that. This is now with a non-zero epsilon, the coupled dispersion equation. Coupled dispersion equation. Okay, so we will see more about this in the next class. Thank you.